Hello again. So today we're going to be doing an intro to electrochemistry for standard levels. Um, Electrochemistry is the study of the interchange between chemical potential energy and electrical energy. This can occur in either way, either direction. A voltaic cell is a device that is used to convert chemical potential energy into electrical energy. It's a battery, more or less. Um, they work on the principle of uh, they work off the principle of displacement reactions generally. Um, and so normally when all the reactants are mixed, the electrons are transferred in particle collisions and the electrons are released as heat if the reaction is exothermic. Heat is not electrical energy. That's the problem. So consider that reaction here. So how do we generate a current from this reaction? Now, the way we can do that is by separating them, but basically forcing the reaction to happen through a wire. So if the chemicals are separated and the only way they can interact is by a wire, which remember, since wires are metals and have delocalized electrons, you can essentially you shove one in, you shove an electron in, and an electron will pop out the other end. Now, if you can force it to happen by that way, then success, we have a working battery. So that's sort of the principle of how it works. Now, in the real world, what would happen is that say a particle from the say we'll get into the so say that the zinc a zinc atom here no collides with the electrode at its end of the at its end, and it collides so fast that it actually transfers two electrons to the to the electrode, and it leaves off as an ion. All right, perfect. Now the problem is that zinc is a metal, right? And we know that with metals that you can't have more electrons than protons. So what will happen is that those electrons will displace electrons within the metal, which will eventually displace electrons within the wire, which will displace electrons along the wire to the other side, where those electrons can be picked up by an ion that reduces on the other side via another electrode. That's sort of how it works at a very at a microscopic level. So, however, another thing you need a semi-permeable membrane in order for. However, this is not enough. You also need a semi-permeable membrane, so or some way for ions to transfer between the two half cells, as we will call them later on, the two solutions. So the reason you need it is essentially if you don't have it, you will violate Kirchhoff's uh, loop loop rule. You won't have a closed loop, um, and you need a closed loop such that the basically what you'll have is current can go one way, but it can't go back the other way, and you will have a closed loop. And a circuit is essentially a closed loop. So you need some you need to complete the circuit more or less. So otherwise, you violate Kirchhoff's loop rule, which is the sum of all voltages is zero in a loop, which that wouldn't be the case because there would be a potential difference across the loop of whatever that potential difference was. As we'll go into higher levels, we'll discuss cell potentials and spontaneity. That cell potential would be the difference in voltage, which you're not allowed to have by the loop rule. So we need a semi-permeable membrane such that we can allow the flow of ions to essentially close the loop and complete the circuit. However, um, we need to prevent extensive mixing of the two solutions. So we need some sort of semi-permeable membrane, or a salt bridge is generally what is used. So a salt bridge is sort of a glass bridge that links the two, and you fill it with some ionic compound. It doesn't necessarily have to be ones that partake in the reaction. The idea here is that you balance the charge on both sides of the loop, across the loop. Um, Oxidation occurs at the anode, which is considered to be the negative electrode in a voltaic cell, and reduction occurs at the cathode. Um, the oxidation and reduction occurring at the anode and cathode is always true no matter what, so it's worth remembering. So the way I remember is anox and red cat. That's sort of a mnemonic device I have. So anox, you know, just imagine an ox, and an is short for anode, and ox is for oxidation, and red cat, like a cat that is red, um, red for reduction and cat for cathode. Um, um, The way I remember the mnemonic device for the charge is on, so on, oxidation, oxidation negative, so oxidation no, and and cap, sort of. Yeah, that's the way I'd like to remember. I think I remember it. So and cap, so anode negative, cathode positive, and cap. Pretty easy. If you're into politics, to remember that. Um, and yeah, that's sort of the way I remember it. Now, that's the way I remember it for voltaic cells. For electrolytic cells, which we go on to discuss later, uh, the way I remember it is just it's backwards. So since everything is more or less backwards, I just flip things around and there you go. You got what you want. So here's an example of a zinc copper voltaic cell. Here is a semi-permeable membrane. Here you have a solution of zinc sulfate and a solution of copper sulfate. And here you can have SO4 ions move to balance the charge. Electrons go through the wire, and you have a voltmeter. In this case, it reads 1.1 volts. And there you go. Standard state voltaic cells are voltaic cells that are 25 degrees centigrade and have concentrations of 1 molar of each of the thing on both sides. So that's the last thing I want to cover. For an electrolytic cell, it's the opposite of a voltaic cell in that electrical energy is converted into chemical potential energy. So you use it to reverse reactions. So an electrolytic cell is the opposite of a voltaic cell. The same basic cell design can be used for another electrolytic of voltaic cells, but the determining factor, basically you have to force a voltaic cell to run backwards. And you do this by a use of a power supply. And electrolysis is the process in which a current forced by an external power supply causes a chemical change in a set of chemicals that would otherwise not happen. For example, recharging a battery. That's an example of electrolysis. Producing pure metals. That's another example. And the creation of chemical potential energy is synonymous with making products that are more reactive than the reactants. So careful consideration must be made. So very reactive metals are generally made via electrolysis, and of a molten salt that causes cations of the metals to be produced. So here we have the redox equations. So you need to split it into half reactions. So at the cathode, we have oxidation. But remember, since this is the electrolytic cell, it's backwards. So it's the metal that's oxidizing. So no, it's the metal that's being reduced. So you add electrons here, and it's the non-metal that is oxidizing. So you're removing electrons from this to form pure chlorine gas and 2 electrons here. So here is a simple diagram of an electrolytic cell. Here is molten sodium chloride. Here you have an anode. Here you have an anode. Here you have a battery, which you connect the terminals to. And if you connect it in the opposite, you connect the terminals to the battery, and then the battery will force an external current such to cause electrolysis of the molten salt. Here's a bit more complicated diagram, and one that you would probably use in industry. So here you have an anode. Here you have a cylindrical steel cathode. So the oh my god. All right. As I was saying, so here's the cathode. Here's the anode. You bubble Cl2 gas out of here, and you pump out your molten sodium out here. Here's where you put your sodium chloride. And yeah, that's sort of how it works at an industrial level. Remember, oxidation always occurs at the anode, reduction always occurs at the cathode, which for a voltaic cell, for an electrolytic cell, the anode is the positive terminal and the cathode is the negative terminal. If you remember AND cap, remember that anode is negative, and since a electrolytic cell is opposite voltaic, you would just flip it around, so anode is positive, cathode is negative. That's how I remember it. And yeah, that's sort of it. You don't cover a lot for standard levels, but for the higher levels you do quite a bit. So that's all the electrochemistry you need to know. Thank you very much for watching.